Ever looked at a grid and felt like you were staring into a box of boxes? Well, today we are going to stop just looking at the grid and start mastering it. Welcome back to the channel. I am Supratim, your coach here at Techmine Guru. And today we are diving deep into BSL Lecture 10, The Art of the Grid. Whether you are preparing for interviews or just want to sharpen your problem solving skills, understanding how to navigate and transform 2D matrices is essential. From basic traversal to that ultimate 90-degree clockwise rotation, we are covering it all. Here is what's on our agenda for today. First, we will define a 2D matrix actually is. We will look at syntax and declaration across C++ and Java and Python. We will learn to navigate the grid using rows and columns. Then we will master diagonals with some clever optimization locks. Finally, we will tackle the ultimate transformation, that is rotating a matrix by 90-degree clockwise. So let's start with the basics. Declaration and the storage. Depending on your language of choice, the syntax varies slightly. In C++, you can simply mention it like int matrix of n of m. In Java, you have to define it with new int. And in Python, we can initialize it using a list comprehension like this. Here, n represent rows and m represent columns. To move through a matrix, you have to understand the coordinate system. We define n as our rows and m as our columns. The top left corner is 0, 0. The top right corner is 0, m-1. The bottom left corner is n-1, 0. And bottom right corner is n-1, m-1. So here is the golden observation for moving through the grid. When moving in the ith row, the row number stays constant while the column number changes from 0 to m-1, right? Similarly, when moving in the jth column, the column number is constant and the row number changes from 0 to n-1. So just have to remember that when we are moving in the ith row, our column will change, and when we will move down the jth column, our row number will. Let's put that into practice now. So how to calculate row-wise sum? To get the sum of each row, we run an outer loop from I is equal to 0 to n-1. Inside that, we reset our sum to 0. Then we use an inner loop from j is equal to 0 to m-1, and we add up all the elements into the sum, and then we print the sum in the outer loop. So if we see, the row-wise sum is 1, 5, 7, whose sum will be 13. Similarly, when we go to this row, it will be 2 plus 8 plus 9, which is 19. And when we move to our third row, which is 7, 6, 2, and we sum up all the things, we get 7, 6 plus 2 as 15. So what is the time complexity here? Time complexity is O of n cross m, since we have n rows and m columns. And what is the space complexity? Since we have not taken any extra space, the space complexity is O of 1 only. So similarly, we can have the column-wise sum. The logic is similar, but we flip the priority. The outer loop now iterates through column first, and the inner loop iterates through rows. So if you see 1 plus 2 plus 7 gives you 10, right? Similarly, 5 plus 8 plus 6 gives you 19. And similarly, 7 plus 9 plus 2 will give you 18. Now let's look at the challenge 3, the diagonals. Specifically for square matrices. So for understanding diagonals, we generally prefer to talk about square matrix, in which n and m is equal, which means the square matrix is of n cross n. So here we have two diagonals. This is called as main diagonal, and this blue one is called as anti-diagonal. So how do we code for it, for printing the diagonals? So if you see closely this main diagonal, you will see that every time in the main diagonal, when we have to print, the I is equal to j. Since this will be 0, 0, similarly this will be 1, 1, this will be 2, 2, this will be 3, 3. And if you closely look on the anti-diagonal, you will realize that this is 0, 3, this is 1, 2, this is 2, 1, and this is 3, 0. So if you see the I and the j, the sum of both will give you the length of the square matrix. Since you can see that 0 plus 3 will give you 3, 1 plus 2 will give you 3, 2 plus 1 will give you 3, and 3, 0 will give you 3 only. So this is the only observation which we need to consider when we are considering the case of anti-diagonal, right? But since we are running two loops here, and we don't like time complexity as O n square, so let's see how we can optimize this. So here, if you see, if I is equal to j, can I say if I iterate through one for loop only, and I can print the matrix as matrix of I, comma I, right? That will give you main diagonal, right? Now, for anti-diagonal, you have seen this formula, right? So can we express j in terms of I? So if I plus j is equal to n minus 1, then we will get j is equal to n minus I minus 1. Simple mathematics, right? So instead of j putting here, we have put n minus I minus 1. So this separate loop we have to run 2 times, and which will bring our time complexity from O n square to O of n. So now we don't need an inner loop for the same. So we have optimized for the main diagonal as well as the anti-diagonal also. Now let's move on to a new problem, a little difficult one, where we have to print all diagonals starting from right to left like this. So for handling this, we will divide our work in 2 halves. The first half, if you see, will always start from the 0th row. This, and this will start from the 0th row. And the second half will always start from m minus 1th column, means the last column. So the other diagonals will start from this only. If we have 5 cross 5 also, then also we could have seen the same. So finally, the first half start from 0th row, that is 0, 0 or 0, 1 or 0, 2 or 0, 3. And the second half start from m minus 1th column, that is 1, m minus 1, 2, m minus 1, 3, m minus 1. So if we have seen these 2 patterns, we can extract out the code in 2 halves, right? So now for first half, if we have to write the separate code for the first half, then only our column will change, right? That's why we have started the loop from j is equal to 0 to m minus 1. And since we are always going to start from row number 0, that's why row is equal to 0 is kept and column is equal to j is kept, right? So that every time while printing the diagonal, we can assume that j has been taken, right? So this will also include this too as well. So inside the for loop, we run another loop where our boundary condition is r should be lesser than n, right? Because in the r, we will move to till here, right? And c should be always greater than 0. The column should be always greater than 0. And since we are going from right to left, when we are coming down, the rows will increase, right? And when we are going left, the columns will decrease, right? That's why r plus plus and c minus 1. So this part will print all diagonals from 0th row. So once this half has been done, we will start thinking of the remaining part, which is this one, right? If we have seen properly, the second half will always start from 1 and it will keep moving towards down. And it will always start from the last column. It will never start from any other column. So that's why we are running a loop from for I is equal to 1 to n minus 1, means we are coming down from 1 to 3. That's why we are iterating a loop from I is equal to m1 to n minus 1, and keeping r is equal to I is the same reason for that. And similarly, since we are always starting from the last row, we will keep c as c is equal to m minus 1. So now again, the boundary condition is same. We have to check whether r is lesser than n or not, and we have to check if c is greater than 0 or not. And since we are coming down, that's why r will always increase, and since we are going right to left, the c will always decrease. So this part of the code remains the same. So this is how we can print all the diagonals in right to left manner. Also, for remembrance, you can memorize this, that total diagonals of any matrix is given as m plus n minus 1. So next we will understand about matrix transpose. This means converting rows to columns and columns to rows. Now in this, matrix of I comma j will become matrix of j comma I, right? So if we simply run a loop from I is equal to 0 to n and then j is equal to 0 to m, we will simply double swap it, right? How? So if you iterate through the whole matrix, you will swap everything twice and end up right back where you have started. Because in the step 1, you will swap from 0, 1 to 1, 0. After step 2, you will again swap from 1, 0 to 0, 1. So to fix this, we can only traverse the upper triangle like this one. So that's why in this current program, I is running from 0 to n minus 1 and j is running from I plus 1 to n minus 1, so that we always run the upper triangle, because these diagonals will stay as it is, and this value will swap it here, this value will get swapped here, this value will get swapped here, and this value will get swapped here, right? And the diagonals will remain the same. So since we are not taking any extra space in this and we are just swapping the logic, so the space complexity is O of 1 and time complexity is O of n square, right? And also transpose matrix can only be applied in a square matrix. So this is like in place swapping. Finally, the main problem statement: how to rotate in 90-degree clockwise direction. So let's understand that with an example. So here is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. After rotating it clockwise, this 1, 2, 3 will come here, this 4, 5, 6 will come here, and this 7, 8, 9 will come here. How do we get this? So if you closely look at this, we can break the things into two halves. First, we can transpose the matrix, and then we can reverse each row. Let's see how. So if we just transpose the matrix, what it will be? So while transposing the matrix means 1, 2, 3 will come in the column, 4, 5, 6 will come in this column, and 7, 8, 9 will come in this column. The transpose is done here. Now, if you just simply reverse the rows, you will get 147 as 741, 248 as 852, and 369 as 963. So can you see that we have got what we wanted, right? So rotation in 90-degree clockwise will only include the transpose matrix code, which we have learned in this one, which is giving a time complexity of O of n square, and we have to reverse individual row, right? So just we are iterating the row, that is from for I is equal to 0 to n minus 1, and just we are calling the reverse function, which will reverse an array, basically which will reverse this particular row one by one. So to wrap things up, let's look at our complexity. Printing row wise or column wise sum, the time complexity is O of n cross m, and the space complexity is O of 1 only, since we are not taking any extra space. When we are dealing with printing of diagonals, the brute force was giving us as O of n square, and when we optimized it using I plus j is equal to n minus 1 approach, we got time complexity as O of n, and the space complexity remains the same. While doing transpose, we have to iterate into both the loops, that is from for I is equal to 0 to n minus 1, and then for j is equal to I plus 1 to n minus 1. That's why time complexity is O of n square. And in the rotation, it is O of n square. Why? Because this is taking O of n square, this one is taking O of n, but reversing an array will internally take O of n again. So the complete logic will take O of n square plus O of n square, which we got from the transpose. So the time complexity here will be O of n square only. And since we are not taking any extra space, so the space complexity is O of 1. That's it for today's deep dive into 2D matrices. If you found this breakdown helpful, make sure to hit that subscribe button and join our community here at Techmine Group. In our next lecture, we are going even deeper into the machine with the basics of bit manipulation. So with this, I am Supratim signing off for today, and I'll see you in the next one. Till then, keep coding, keep optimizing, keep learning.